also something which might be effective for the student.
Thank you. Good afternoon, dear children and colleagues. Let me introduce my research. Three-chamber cluster group with outline source amplification for improving frequency control of surface acoustic wave devices. Motivation. Development and improvement of surface wave acoustic devices is actual task for production of cell phones and other wireless applications. Some devices consist of piezoelectric material distinguished between two electrodes and acoustically isolated and surrounded medium. Thickness of this piezoelectric layer defines the oscillating frequency of the device. Piezoelectric fields with thickness ranging from several micrometers to tens of micrometers oscillating the frequency from 0.1 to 10 gigahertz. Aluminum nitride and zinc oxide are two common piezoelectric materials used in startup. The standard process of its production consists of the following. At first, aluminum nitride deposition for the aluminum nitride deposition is used AC magnetron. The second part of the process is the following. The thickness of aluminum nitride deposit layer scanned with 3 radial lasers interferometer, and its thickness usually varies greatly varies over the area of the vapor. To decrease the spread over the thickness, the treatment process was applied. The process is established by exposing the aluminum nitride layer to KEP, argon ion beam. The local sputtering of aluminum nitride layer is based on topography method using an adjustable focus TCI source and scanning vapor mechanism based on radial laser interferometer. The economical impact of this technological approach really depends on erosion rates in a given local area. Our challenge was to develop simple, compact, steady-state, and high-flux sensors with focused handling and long time of continuous operation. On our best knowledge, no exciting focused handling sources would meet the requirements for this processing technology. Therefore, we adopt the electrical space propulsion to achieve high edge rates for small surface area. The principal scheme of an odd-layer cluster is the following. Its construction provides P cross B fields. There are electronic bit layer in this field, and the main ionizing process occurs at this electronic bit layer, and the ions are accelerated in the circular ion beam by electrical field. To adopt the transfer for high current density, it was necessary to convert cylindrical type of the beam to cone light. To implement the ballistic focusing, usual plain cathode and anode were replaced by a new one with special shape with channels which provide cone light beam. To improve the focusing, the magnetic lens, magnetic reversible system was used for this type of the source. The energy distribution function was measured by cylinder type energy analyzer, and we can see that it close to maximum amount. On the previous slide, you can see that a low energy spike of energy distribution function is cut off. It's cut off by some magnetic field in the neural plane. So the ions of light ions like hydrogen being bending towards the cathode. So that is the reason of low energy spike of ion distribution function is cut off. Also, the beam intensity was measured by sputtering CO2 layer on the sea vapor with argon and hydrogen ion beam. We can see that beam intensity is well concentrated within the spot of nearly 12 centimeters phase, nearly 3 millimeters. Also, it was performed the experiment of the burning the sea vapor, and on these pictures you can see the rear view of sea vapor of the following thickness, which was exposed to the 30 million years of ion beam. On this picture, you can see the glow of Oleksii wafer, and this glow is defined by an intensity temperature gradient. Central yellow spot corresponds to peak intensity of the ion beam, and the resulting etched hole in the wafer is about 1 millimeter in diameter, which is in good agreement with the previous spotlight film result. So this ion source allows high radiation over small surface area, about 3 millimeter. Location of the layer with high rays is a key feature of this technological approach. On this slide, you can see the results of numerical calculation of impurities mass separation. Because of reversible magnetic field, it is this nice compatibility of to separate the different ions, the ions of different masses. So on this picture, we can see the results of numerical calculation for different distance between the coils of 20, 40, and 60 millimeters, and for different ion mass. And this is the radius in the focal plane of hydrogen ions. And on this picture, you can see the results of experiment which was performed with stainless steel coated with TN, and the cyclic sand was used as a working gas. In the gas discharge, the molecule of cyclic sand is divided into the hydrogen ions and the CH group ions. So as a result, on the surface you can see the area number 1, which is spotted by hydrogen ions, the area 2 and 4, which corresponds to CH film deposited without ion component, and the area 3, you can see the deposition of diamond-like film stimulated by CH ion. So due to magnetic focusing, the impurities can be separated, providing pure light ion beam transport in the center. On this slide, you can see the two pictures of dependencies of ion beam current as a function of this charge voltage, and the ion flux is also plotted here. The ion flux was calculated assuming that the beam spot is a 3 millimeter of diameter. One of the interesting features of such a kind of accelerators here that the ion current and discharge current is proportional to pumping speed. On this picture, you can see the dependence of ion beam current as a function of discharge voltage at different pumping rates. The experiment was performed with argon, and curves 1 and 2 corresponds to beam and discharge currents at 300 meters per pump, and curves 3 and 4 corresponds to beam and discharge currents with 1,200 liters per second per pump. On this picture, we can see the gas discharge power as a function of airflow, which was performed on 300 liters per second turbo pump. In the following picture, you can see the total argon ions beam current as a function of discharge voltage, which was obtained on 1,200 liters per second turbo pump. From this slide, we can make the following conclusions that such a high ion beam current is well concentrated in a spot of 3 plus minus 1 meter in diameter and provide high enough current density power 500 milliamps per centimeter squared and high rates as a result. So the three-chamber cluster tool is such a kind of source is able for high precise and high speed related to large vectors treatment. On this slide, you can see the figure on the amount of devices as a function of their working frequency obtained from one wafer is plotted. We can see that after the first, the curve 1 corresponds to initial deposited there, the curve 2 corresponds to the first stream process, and the curve 3 corresponds to the second stream process. We can see that the first stream can give 5 weeks improvement, and the second string provides another 4x improvement. So as a result, the total frequency improvement should be as big as 20 times and maybe higher, which has a direct impact on overall economical efficiency of this technology.
3 minutes.
This three-chamber cluster loop is capable for high precise and high-speed large record streaming. High-rate fetching is a key feature provided by this source, which defines overall economical efficiency of technology approach. The source generates the ion beam current stated in a spot of 3 mm diameter and provides current density up to 500 milliamps per second and above. Many gas discharge characteristics of the source are measurable on the system with different pumping rates. Increase of the pumping speed and the gas flow leads to the increase of the ion beam current and etching rates as a consequence, without distorting the ion beam profile. Applying double jigging process results in up to 20 increase of production of aluminum nitride surface acoustic wave devices, which meets the requirements of this RF needs. Thank you for your attention.
Thank you, especially for being precise on time. Questions or remarks?
I have one question. How do you measure the incident flux of the ion beam?
The radiant flux of the ion beam was measured by ion beam current, and we know also the profile of ion beam.
With input current and voltage? Okay. Ion beam current and?
We know ion beam current, and we know the beam profile, so we can calculate the ion flux. The ion flux is calculated.
That you did in the beginning.
No?
You calculate it.
We measure the total current of our total current, and then we
Maybe one question from me. Sometimes these ion thrusters are, so to say, frequently showing in the plume area instabilities. That means you see rotating spokes as where the effectivity of some of the thrusters are strongly affected. Do you see indications of instabilities in this system?
at some rate of magnetical field in the main coil and the focusing coil, the stability occurs. But these experiments were performed out of this range of magnetic field.
And the eigentime of the instability is roughly the coupling to the transport time of the neutrons, milliseconds or something. When you see these instabilities, these are kilohertz.
Yeah, these instabilities near we measured these oscillations, and the peak of the oscillations was nearly 700 kilohertz.
That coincides well with the typical movement. Good, and thanks to speaker again. As we move on